Good morning, everyone. Welcome to 8.4. Hope you had a good time with Jake in the classes bonus lecture. Hope that was interesting. I saw a handful of you were going, pretty much everyone here, which is good. I hope it gives a taste of just a different type of topic around programming, because it is just a very different thing overall, and something you'll probably be exposed to more down the line. It's actually a common question we get, is like, is Python an object-oriented programming language? And the answer quite often is just, who knows? There's differing opinions on it. There's a big difference, though, of course, between languages that are object-oriented and like have those capabilities. But we're talking about something arguably a little less exciting today, which is property-based testing. This is the last of the testing topics we have in the course. It's arguably probably like the least important in the scheme of things because, again, as we get later in the course, we tend to, I guess, tackle things that are a little less critical. That number should be 0.4, sorry. I probably uploaded the wrong PDF. But today is a topic around, like most of what we've talked about with testing so far has been really focused on a very basic level of testing, which is kind of just writing your own tests. Now, at scale and in bigger projects, you're often going to be using far more advanced tools to help you automate your testing. It's not something we cover much in this course at all. It's something that we just kind of allude to like this. So good testing takes a lot of time to write, and you might have seen this through your own project, where if you want to write lots and lots of tests and lots of edge cases, you just have to write a lot of code, and the more code you write, the more prone it is to the tests themselves having bugs, right? Because every line of code you don't write is bug free, and you also might just miss them. So you might write a lot of code and your code might be a bit buggy, and you might miss some other edge cases too. So we need a way, or we need a number of ways to try and solve this problem and actually essentially test at scale. Property-based testing is a topic that essentially covers that. So what property-based testing is it's a method used to help generate test data for you. Because a good example to lean on here is, say, your auth register route or your auth login route, whereby you are often maybe testing a whole bunch of passwords or a whole bunch of first names or a whole bunch of last names or a whole bunch of emails that all fit a particular format. But you don't want to write out, a million different use cases, because I bet for most of you, your like password checker or your first name checker in your tests is often just going to be like one or two or three things, right? Test Hayden and Jake and Alex or something like that. So we need a way to meaningfully generate test data, and we need a way to kind of report test failures to us in an understandable way. So a lot of this is really focused on just generating test data. I don't think we're going to go till 11 on this because it's a relatively short topic. So this is where property-based testing comes in. So property-based testing is a method of testing where tests are defined as general properties. What that means is, you say, okay, for this test, here is a property about, I want to populate the first name or the last name. It's essentially just an abstraction where you're not writing things out manually. So test input is generated automatically by supplying a strategy. We'll talk about what a strategy is soon, but a strategy might be, I want to test all of random strings up to 20 characters. That's just a strategy. And what the testing framework does is it actually runs the test many, many times for you as an abstraction to ensure that the properties are true for each input. What we mean by properties are true for each input is, say that you have a particular test that's trying to test if a register function could be called validly. The property of that test is a register function, you expect it to succeed. And you're trying to give a whole bunch of automated generated inputs into that. In the event of a test failure, just like PyTest, the framework needs a way to kind of shrink down the problem to just telling you what exactly failed. Because in a normal test, you might have 3 different examples, but when you're doing property-based testing and there's all this generated input, because your functions are being called potentially hundreds or thousands of times, if you get a whole bunch of them failing, you don't want to get 1,000 different errors in your terminal when it comes to actually running it. So there's a library that we use in this course called Hypothesis. Hypothesis, I'm pretty sure, is a library that it's at least partially maintained by some academics at the Australian National University in Canberra. We had a little call with them a couple of years ago, which was really interesting, but it's essentially a property-based testing framework library, and it can be installed with pip3 like this, and I'm pretty sure it's also part of our requirements.txt. Let me just grab the file on my other browser. I'm pretty sure Hypothesis is part of, yeah, it is. So Hypothesis, the library, is part of the libraries we give you. So you can actually, you already have this on your system if you pip3 installed it here. You can obviously go and pip3 install it locally or anything like that. And what we're going to do is we're going to have a look at an example of where you can actually use the Hypothesis library to test something. So I'm going to pull up some code here. And we're going to have a look at a bubble sort. Now I know that for a handful of you who have done 2521 or are doing 2521, you'll say, I know what a bubble sort is. And then there'll be another handful of you here who are like, I don't know what that is. So maybe we'll just very, very quickly recap that. For the small number of people that don't know what a bubble sort is, it's essentially a sorting algorithm whereby you take a list of numbers that are in the wrong order and you move through it. And anytime you see numbers in the wrong order, you just swap them around side by side, and you just keep doing that until it's swapped. It's kind of like I always like to refer to it as it's the simplest kind of swap that you would do if you'd never tried to sort numbers before and I sat you down with a Python program that didn't have a sort in. I just said sort these numbers, because you just loop over it and you just keep going. It's kind of like a little bit brute forcey. So what we have here is we're going to have a piece of code inside of our, oops, I just opened up bubble sort. We have a piece of code here inside of our 8.4 folder that, if we ignore this for a second, we have a bubble sort function, right? And we can also ignore this up here. So we have a bubble sort function. It's relatively straightforward. It takes in a list of numbers. We copy that list of numbers, and then we do the bubble sort algorithm, which is two loops, one after another. And then there's like an if statement inside. So essentially, this first loop is saying go until sorted. This loop is saying go through all the numbers. This loop is saying if any pair are in the wrong order. And this loop is saying swap them to the right order. So it's always swapping adjacent pairs, right? And we can try this, use this function too. So if we create a list, say a list of random numbers like that, and I'll just go and put commas between them all. Oop, that's full stops. Like this. And then I'll just say print bubble sort, pass in those numbers, and let's see what it does. So we'll open up our terminal, we'll bring it up over here, and we'll just run, we'll go inside 8.4, we'll run Python 3 bubble sort, and there's our numbers sorted, right? So it's a relatively straightforward sorting algorithm. Diorora says this is what we need for the inverse lab, right? Yeah, that's correct. So this is the stuff that you'd be using for the inverse lab, because I do think there's reference to property-based testing there. Now, after this, well, you might say, I'm going to go write some PyTests. And you say, okay, well, that's easy enough. I'll say define test bubble sort small numbers. Now, obviously, you're used to this because of your project. You have your test. I go and write my list here. I then say, assert that bubble sort of my list equals, whatever this is, 1, 1. I know I could just look at the thing on the right. 5, 5, 5. What is it? 8, 8, 9 or something? 1, 1, 3, 3, 4, 4, 5, 5, 5, 8. Oh, okay. Surprised that worked. And now when we run our program, obviously nothing happens because it's PyTest. So now I need to run bubble sort on it there. PyTest will run. It'll tell us that we passed because things are correct here. One thing that's worth pointing out too, on the topic of writing more advanced tests, I think this was touched on the forum very loosely, but one kind of question that comes up every term, which I love, are people saying like, how do I write tests when I don't know what the output should be? And this kind of comes up in other courses as well, but since we're talking about testing so much in this course, one thing I want to kind of really reiterate here is that sometimes you'll write tests by hand. You'll say, I'm going to write a function that should have some kind of behavior, and because that behavior is so simple, and my test data is so small, I can actually just manually, visually write out some test cases. Another way to test though, so slight tangent, another way to test is to write simpler solutions of what you have. And this one is really, really common. And I know a bunch of 2521 students would have heard me say this as well, but it's like, if you're writing a new type of sort, let's call it like, fancy, schmancy, dancy sort-tastic fun times. Like if you're writing some kind of sort here that takes in some numbers and it does some, magic and then it returns some numbers. And this magic is really complicated, right? It's, it could be like super long lines of code, lots of different use cases, super optimized for some, really aggressive time complexity. The thing is that you trying to say then write something to sort many numbers could be very hard because you might just not know how to do it all manually. So what we often do, obviously for this one there's things online that sort numbers for you, but we'll often actually write a simpler algorithm to test those numbers to generate test data. So it's actually very common for, say, a really good programmer who can kind of confidently write a simple piece of code that they kind of can look at this and step through it manually and say, I know this is right. And it's really, really simple. Maybe it's like a really boring, pathetic solution. Like it's, 3 or 4 or 5 for loops nested that just goes and checks every single random thing, right? Like you think about all those different scenarios. Sometimes we write simpler versions of our code that we can kind of check manually to generate test data for our more advanced versions of code. So there's lots of all these different kind of ways to test. A really good example of this would be, I know I've mentioned this before, but there's the programming challenges course at UNSW, and this was a very common theme in this course, which was that you had to go and write very, very complex algorithms that would do very, very complex things, and that would be really hard, but they were often really simple algorithms like a sort or something, which everyone knew how to do, so you could actually go and write like a crappy version of it that you knew was right to generate test data for your more complicated solution. Now that was slightly tangential here because I was just trying to explain, we do get the question sometimes of people being like, yeah, this is all well and good, but how do you generate test data if you're sorting a list of 1,000 items? Because you're not going to write out 1,000 items manually. Sometimes we get software to do that for us as well. Sometimes we write software to do that for us as well. The most important, I guess, rule to follow in the world of testing is that, what the kind of capability or function you're testing against some data, that data should have been generated from a simpler method. Whether that's you writing it out manually, whether that's a simpler function, whether that's something you find online, whatever. Now, back to hypothesis though. This is all well and good to just say, here's my test, but it's not very thorough. It doesn't really test that many use cases here. So we're going to use hypothesis to try and test stuff for us. Now, the first thing we want to test is that the lengths are the same. This is a relatively straightforward thing to test. I could have actually, tested this up here ourselves, where I say, here's my list, and I'm just going to check, is the length of what bubble sort returns the same as the length of, the list I pass in. In fact, I don't even need to do this. I could just say list here. Are those two things the same? I could run PyTest, and yeah, there you go. But again, we're only testing one thing here. So if we use hypothesis and we use a couple of hypothesis decorators, because hypothesis is built on decorators, that's why we teach it this late in the term, I've actually got a different kind of thing here, and I'm going to get rid of this assert, where this function test length takes in nums, and those nums are generated by hypothesis and run for you. So if you normally look at this, you think, I've got one test file here. But what hypothesis does is you use the given decorator, which takes in a strategy. And this syntax is a little bit weird, and it's very custom to Hypothesis as a library. But if we actually like unpack what's happening here, right? So I'm just going to remove some of these lines again. And let's have a look at just this given decorator line for a second, because there's a few things going on. The first thing going on is that you can see that given is a decorator that takes in a function called list, which takes in a value called this.integers. So let's actually just print that out. Let's actually see what strategies.integers is, because this all comes from the Hypothesis library. Okay, nothing exciting here, right? Let me just make this window a bit smaller. It's just printing out integers. That's weird, right? Who knows what that is? Let's keep exploring this together. So now I can see that what the decorator is given is actually this strategies.lists and then that. So we run that. Now I get list.integers. List integers. So what's actually happening here is that what these abstractions are, these strategies.integers and these strategies.lists, these are simply abstractions for instructions that the @given decorator takes. And what the @given decorator does is it says, given these strategies, apply them to a particular function. You can ignore this verbosity thing. I might even get rid of it for now. So if we keep things really simple here and we say we've got a test function that there's this kind of nums generator. Think of this like PyTest fixtures, because most of you dealt with that. This is like fixtures, except the fixture is more complicated, because your fixture was you saying, I'm going to go write an abstraction over here where I'm going to go generate or prepare the test. This one is saying, no, let's use a library to generate many test values at once. So let's see what happens when I run PyTest now. Okay, it says PyTest and everything passed. That's somewhat expected. Wondering where the print is. Maybe we need to put this back. Maybe that's the secret. So on the topic of decorators, just before we look at the printing, one thing that we didn't touch on in the last lecture with decorators was that you can actually have multiple decorators kind of stacking on top of each other. And they really do form like a kind of wrapping bubble, right? Because with decorators, we learn that you have a function, and when you decorate it, it's like wrapping something around it. So if you decorate a decorator, it's like wrapping something around the wrapper for the original function. So settings is another decorator from the Hypothesis library that essentially specifies how much information you want to see when tests succeed or tests fail. And this one here is actually telling you what you want to pass into the test. So let's put the assert back in, and let's see how this goes. Oops. Sorry. Tabs, indentations. Okay, so this still seems to work. Bit unclear though as to what's actually going on here in terms of the print, because it says there's only one test being passed, but we've been told before that the Hypothesis here is running a whole bunch of tests. So let's try and dig into this a little bit. We can see we're calling the bubble sort function. What happens if we try and print something here? Does anyone have any ideas? How are we gonna? I mean, you should all know this. How are we gonna extract information from this? I want to actually see what's happening with my test. How do you guys check this out when you're running PyTest, right? How do you figure it out? Yeah, like how do you debug it? I'd actually be really curious, because I'm sure a number of you have kind of run into a situation where you actually wanted to put a print in a PyTest, see what it gets out. Is the problem Hypothesis here? We can try it without Hypothesis. Let's just try it like this. Nums equals 1, 2, 3. Yeah, so Matthew's on the kind of on the money here. It's like PyTest automatically hides standard out if it works, right? Now there's a couple of different solutions here which I think are funny. The first one, well, not the first one, is like Roy said, yeah. So some of you have found like the right way to do it, and some of you have found the wrong way to do it, or I should say a different way to do it. Someone's saying, well, we can get this, we can print it out by simply, I'm going to put a clear in front of this as well. We can simply put an assert that fails, because PyTest will hide standard out if it succeeds. So I can say assert false, and then now it fails, and then we're going to get our print. So you can see captured the standard out call. Cool. So a few of you have done something like that, and then separately, Decorators talked about the -dvv flag. So if I go pytest -vv, I actually haven't used this flag much. Is it -vv or is it just -v, or what is it? I actually normally do the assert false, don't worry. I'm in the same boat as many of you. But I'm curious what the actual pytest verbose is. -v. Okay. Am I missing something here? Is it just off screen? Don't know. That's okay. We can keep it simple. I'm sure I'm missing something small. So if we look at something like this now, and we have our test, pytest-s. Oops, got to get rid of that. Yeah. I'm not. That's okay. Let's not worry about that for now. I don't want to get distracted. So we have our test. We say it's going to fail. Oh, it probably worked. I just got rid of the print. So let's go back to hypothesis. Hypothesis should provide us with these nums. So let's see what happens now if we print these nums. Okay, error, bubble sort, and I scroll up and there's all this other stuff here. They're very verbose flag, test summary, error, bubble sort, interrupted one error during collection because I can't put freaking indentation in correctly, and now we're getting something interesting. Look at all this crap here. Now, if we look at this pytest result, right? So let's just recap. I ran pytest up here. The test session started. The test failed. It failed on line, well, the lines are a bit deceiving, but it failed on the false, as you'd expect. Now we captured our standard out. So have a look at this. What actually happened here was that this test length function was called approximately 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 times, I think, right? And it was called 12 times. So what do we know? Like, we know this about decorators because last week I showed you a decorator where you can decorate a function and that decorator will actually call that underlying function twice. So what's happening here is that hypothesis is actually saying that given this strategy of creating a list of integers, I want you to call the test length function 12 times. However, what is cool about that is when it succeeds, do you remember how it only showed one green dot? So these kind of property-based testing libraries and other more advanced libraries have this capacity to say, take your test function, run it on a whole bunch of input, but if it succeeds, just say that that test passed. You know, that property, you succeeded, you know, testing that property, which in this case might be the length. So the length of this list is the property in this case, and it's like, yep, all right, well, we've tested that property. So the questions now become a bit more interesting around, well, I've got like 2 or 3 empty lists here, I've got all these different numbers, and so forth. How can we tweak that kind of thing? And let me just play around with the flags again, because I'm just not familiar with. See if we can keep it simple. Yeah, so what do we got here? VVS, great. One thing that you can also see here is that hypothesis is actually giving us a whole bunch of information, because we captured not only our standard output before. If I scroll all the way up, God, there's a lot. Yeah, so what's actually happening here is you can actually see that hypothesis is reporting all of the things that it's been doing. It's like trying example this with these numbers, trying example, and there's the standard output there, and then it's like trying example this with these numbers. So we don't actually even need these prints here, because the settings verbosity equals verbose is actually what kind of helps us understand what's going on. Now, just on the topic of verbosity, if you actually look at like, sometimes you might call this log verbosity, it's like verbosity. You will see a pretty standard list of things. I've just gone to the first one I find on the internet because you tend to see something like this. Sometimes they'll be a bit different. and there's some here that are missing that I'm used to and some I don't see, but typically in any kind of logging system or other system that is going to produce output at scale, you have certain levels of verbosity that you specify you want to hear about, and they essentially move from the highest, which is like the strictest in the sense that you only want to hear about the most important things, and then you move down towards hearing about the least important things. The irony of this scale is that if you care about less, you pick the one that sounds more serious, right? Because what this one actually means is that I will only report to you if something fatal happened, if the system literally crashed. The next one says, I will only print to the terminal if there are errors or something totally crashed. And then warning is like, I'll tell you if there's warnings or errors or totally crashed. So it's like they all get, it's not like one or the other. It's like a building up effect. So very verbose means I'll show you very verbose stuff, log stuff, display stuff, warning stuff, error and fatal stuff. So log might typically be key events, like starting test, finishing test, whereas verbose might be like starting test, here's the input, testing ran for 5 seconds. And this varies depending on the application you're using. And in the case of hypothesis as another library, you can see the verbosity here really just refers to how much information there is. And we could look this up too, right? Hypothesis, Python, verbosity, we'll see something online. Hypothesis is a very, very kind of like not big library in terms of, it's not like, I don't know who is this person? Yeah, it's like it's a small band of people. It's not like a massive like library like Flask. But if we look up, verbosity here, it's like, well, they don't even really show me the levels. But most of them are pretty. I would imagine most of them are relatively predictable. Like warning, I'm sure works fine. And you can see in this case here. Oh no, that's just not a thing. Error. I'm not sure where to look this up. Normally I don't change this, but there you go. I guess that's the thing, verbose. Verbose means a lot, that's why we get all these kinds of outputs. So trying example test length with all of this. That can be really useful for our debugging purposes. Some of the questions now come to, what happens if we want to change the length, the number of integers we're passing in, or the types of integers being passed in, etc. Well, we can change this by changing how our strategies work. Before I get to that though, Hussein does have a good question which says, is one of these default or is the default one even less info than fatal? Typically, I don't know what, like the default one would depend on the library that you're using. I'll look it up again just because obviously this is like a hypothesis. Let's just go straight to their pip library and have a look. So on the PyPy site, you can see the hypothesis library, documentation. This is how you can find stuff as well. I might search for verbose. See if it's there. Searching. There you go. See, just a bit of patience and everything's easy. Okay. Alright, that's oddly not lacking. There you go. I'm not sure what the rest are. Looks like normal's the default one. I'm not... Okay, there we go. Just got to read, guys. It's a life lesson. Quiet, normal, verbose, and debug. So this is my whole point. Every different kind of logging system will have certain different names and different degrees of granularity. But this one, quiet, would be probably off. I'm just guessing, and again, it's probably written here as well. Normal's like probably something around the error warning. Verbose is like lots of info. And debug, in this case, debug sometimes might be referred to as the most intense one, which is like something has gone wrong and you need as much information as humanly possible. So let's try this one out here. Okay, well, there you go. Look at all this information here. It's not just telling you like trying this example. It's actually saying, okay, let's try this example test length. It's telling you the number of bytes associated with the data you're passing in. And then it's telling you that, whether it's valid or not, and then exit with run complete after 102 examples. So you see how this kind of works. And then if I go to normal, which is probably only going to complain if there are problems, we get basically nothing. So we'll stick with verbose for now, because that gives us a good amount of information. But how do we change what's being passed in here? So hypothesis, strategies, integers, right? So if I Google this now, Python examples or whatever, and again we could go back to the library to look up strategies potentially. Maybe I'll look up integer. That's okay. There are these different kinds of strategies from hypothesis, and they can take in various parameters. Now, again, I'm just not equipped with this library because I don't use it day to day, but most of it's in the docs, and I have looked it up before. An example with the strategies, HS here means hypothesis, right? We've just imported it differently. So, like, instead of saying hypothesis, yeah, they're using HS here, but we're using strategies. You can actually pass in some values into integers, which I believe are like min value equals 1, max value equals 5. Let's try this one. I think that's how this works, right? And there you go. Now suddenly it's like all of your tests are kind of constrained in a different way. Or if you want to only use large numbers, for instance, you could say, well, let's go from, some big number like that to some other big number like that. And now all of our numbers are going to be very large that we're testing. So there's these nice little abstractions here where it's like strategies.integers is basically just what you might call a predicate that dictates to you what kind of atomic items you want. In this case, what kind of, numbers, characters, strings. And this strategies.lists is what helps you specify, I actually don't just want integers here, I actually want lists of things. So if we, for instance, just had strategies.integers, this would be appropriate for a kind of test that's just taking in integers. So if I run this one now, it will fail because, because the bubble sort's now taking in an integer, right, not a list. So I could try something else like if we get rid of this assert for a second and I just say, assert that nums plus 1 is equal to, or is not equal to nums or something like this. A really simple test. It's like when I run this one now, you can see that our hypothesis called this with just nums here. So like strategies.integers is just a predicate strategy for the library to say, here's a way to generate integers. Here's just a description, a declaration of what I want you to make. And when you wrap that in strategies.lists, that's how you end up now with the kind of ability that's like, now I actually want you to take in entire lists. And you could complicate that further, right? Like I could, as another example, I'm pretty sure that we'd be able to wrap strategies.lists in strategies.lists. I've never tried to do this. It's fun to explore with you. There you go. So this still worked here too, right? We generated lists of integers. So, nums here is a list which contains another list of integers and more lists of integers. So you can see these abstractions make it really powerful and easy to build out kind of complicated sets of data. And then if we look at strategies.lists, this might give us a better, see if this gives us a better page we can jump to quickly, or we can just search the library. Hypothesis, strategies.lists, there you go. Takes in the elements, which is often can be values or it can be a predicate itself. Minimum size, maximum size, unique by, unique equals false. So unique is true. We, as if. Okay, so we can try and play around with this now, right? Where we say, let's get rid of this double list thing because it's a bit weird. Now we can say that list doesn't just take in as strategies for integers, it also takes in a minimum value equals, say, 5, and a maximum value equals 5. So now we only want to test lists that are size 5. Sorry. I've done something wrong here. Strategies.lists. What's the problem? I'm not sure what I've done wrong. List got an unexpected keyword. Let's look at this full error. Min value. Ooh, okay. That's not good. That means this isn't being used correctly. So you can see, let's have a look at it. It takes in the integers, returns a list containing drawn elements, blah, blah, blah. For example, a list, 2 points, unique by... Huh. There you go. That doesn't make much sense to me why this one isn't working. Oh, min val... Sorry, thank you. Yeah, that makes more sense. I was like, I swear this worked when I tried it out earlier. So we got min size there, and now you can see that all the lists are the right size. So you could quite literally constrain this to only test numbers between 10 and 20 that are all size 5, and now we get something like this. But you notice in this case we've got some duplicates like 15. So now you could actually obviously specify as per the library that you don't want to allow, you want to make sure everything is unique as well. So now when I say unique is true, now all these numbers are unique. So really, really powerful declarative kind of libraries, right? And you can use this for strings, because it's not just strategies dot integers, there's also strategies dot floats, there's strategies dot text, I think, you know, so you can like specify what kind of things you want. So now we could say write a test that's like, you know, say we want to test strings, you want to sort strings, and you say, well, okay, I'm going to have a list of my strategy now is going to be text, the min size in this case is going to be say 5, or you know 50, then let's just do 5. The max size will be, think about your assignment, right, like a password or something, you know, min size 3, max size 20 for the actual strings themselves, and how many items in each list do you want to test. Like, do you want to sort? Well, who knows, 5 and 5 is fine as well. So when we run this one now, we're going to run a couple of tests here, which are not just your test length, but now we're running our test strings, and you can see that there's a whole bunch of like different strings here, though they contain some strange characters, right? And you can see that like what is there by default? Well, the alphabet is a set of characters, but maybe we want a different alphabet, so we could try and define our own alphabet here. We could say, you know, alphabet is just maybe, you would normally use an abstraction for this, but you know, this probably works, A, B, C, D, E, F, I'm guessing. Yeah, there you go. So there's your alphabet. Or let's say, you know, you're doing pin codes. You could, I'm sure there's a string dot numbers, isn't there? There's like something from the string library. So now you could test passcodes that are all just numbers. Yeah, great. There you go. I'm not sure why they're all 3 digits. Min size, max size. That's weird. Is that just random? Oh, I think that maybe they sort them by size or something. Not too sure. Lots and lots of tests though. So again, to recap, the main point of this is that you have these nice abstractions which can generate things for you, and you can wrap them within each other. So you can wrap a, you know, an integers abstraction within a list abstraction, and the list abstraction within another list abstraction. And then it will actually call the underlying test function a number of times. And then that underlying test function will pass, and if it fails, you'll actually get a bit of a report. So questions from Gore. What's the most popular property tester? I have no idea. I've never looked into that. Waleed, are we expected to use property-based testing extensively in the assignment as well? No, I don't think you're expected to per se. I would say that it's a good way to, you know, get a higher code quality mark and whatnot, because you might have more thorough tests. I would say it's at least worth trying out somewhere. You know, it can only be good for your marks, I guess. For instance, on the password thing, like password's a good example, because you know, passwords only have so many characters, and you could pass a whole bunch of them into it, which is like a good thing, because like passwords are complicated. You're using a hashing library. How do you know that that hashing library works for all the input you're giving it? I mean, it's probably written in the specification for the hashing library, but it's still worth actually testing, because of, you know, the fact that it's a more complicated thing you're testing. So that's most of it. Yeah, that's kind of it. Do you have any other questions about this? Obviously, there's more to the library. you know, and we've got some other examples down here that are more just testing lots of different integers for bubble sort. Yes. This one's actually a really interesting test. I might just quickly mention this because this example was written by another lecturer previously, which I think is interesting. Is what they're doing here is they're testing what's called idempotence, and I think this is an underrated concept that just doesn't come across a lot of, I guess, students' desks as they're studying. I mean, you probably remember this from maths. Idempotence is the property of a certain object whereby they can apply multiple times without changing the result beyond the initial application. I'm not sure if like Jake talked about this in the HTTP lecture, but when you have post requests and put requests, for instance, put requests are meant to be idempotent, which means that the effect on the state of a system by running it once should be identical to running it twice, 3 times, 4 times with the same input. It essentially means that you have guarantees that if you accidentally run it a few times, nothing will change, right? As opposed to post requests, which are like, if you want to say create a new message in a channel, if you send it 4 times, you're going to get, the state's going to change every time. Sending it 4 times is very different to sending it once, whereas put requests are different. Sending it once should be the same as all the other times. Now, what this test here, for instance, is doing, which is a good test if your system expects this, is it's trying to test the idempotence of this function. And what that means is that you will generate a bunch of integers from lists, and then here you say, you know what, if I bubble sort this once, I expect the same result as if I bubble sort it twice. So I bubble sort it once and then bubble sort that result once. I shouldn't get some other kind of crazy value just because I ran it twice. Yeah, that's probably my last comments here. Are there any other questions? Or are we all feeling okay? It's a pretty simple topic. We really take our time with the lecture because we have a bit more time now. It's not something you need to stress about. It's something worth trying out. Would definitely give it a try in your group, just to see how you can go with it. Cool. Well, thank you in general. Leave some feedback. We might chat for another 5 or 6 minutes since we've got like 5 or 6 minutes till 11. But again, pause the video. Please leave some feedback. That would be great. That's pretty much it today.